Hello, hello, and welcome to page 3 of the notes. And we're going to talk about how we can now find, either the volume or the mass of a three-dimensional object using spherical coordinates. And again, volume only when we're defining everything by the integrals. And the inside of the integral is just going to be dv. All right, so here we have kind of a picture of what we're taking the volume of. It's a spherical wedge, and it's defined. The upper part of the surface is defined by a circle, and the lower part of the surface is defined by a circle. And so it's in between two planes that are circles, and the depth of that is going to be delta rho. The width of the lower is going to be delta theta. The width of the upper, actually the width of the lower is going to be a combination between delta theta, delta phi. When we're talking about that lower region, and so basically what we're going to do is going to be the same thing when we're actually trying to find volume of this. Now, when we're trying to find the volume of this, and we're trying to find a spherical wedge, all right, what we're going to do is the triple integral formula is just going to be, our variables that are going to be defined. And again, this is always going to be defined in this order where our rho, not always, rho always wants to be the inside integral. All right, so here you see rho is the inside integral right there. All right, so rho is always going to come first. Like when we're talking about with spherical, radius is going to come, or not radius, but z is going to come first. Then, these two, theta and phi, are going to be interchangeable, but usually we'll say d theta, d phi. And so the last thing that I want to talk about is, okay, that's how you set it up. But you know how, when we're doing spherical, or we're doing polar coordinates, and we're changing to, r's and thetas, and then we always have r, dr, d theta for like a double integral. We have to always add that in, and also with spherical. Well, in this case, what we're going to have to add in is always going to be, when we're changing the spherical and a triple integral, rho squared sine phi. All right, and the concept's the same as we did. And next class we'll show you, the Jacobian method of how to find it. I'm just going to briefly talk about why it's rho squared sine phi. Well, it's rho squared sine phi because the volume of a spherical wedge is just going to be the arc length of theta plus the arc length of phi times the depth of our wedge. All right. Well, the arc length theta, if you recall from geometry or calc, honestly not calc, but trig, arc length is just the radius times the angle. And so the radius is, and for phi, it's going to be delta phi, that change in that, times r, plus the arc length for theta is now going to be rho times delta phi. And then our depth is just going to be represented by phi. So the change in phi. So delta phi. Delta rho. Too many Greek letters. And so when we are finding volume, what's going to happen is we have all of our deltas, delta phi, delta rho, delta theta, delta phi, and delta rho right there. And that's not plus, this is times right here. So I want to make sure that we know that's times. And so what's going to be left over is rho and phi. Well, again, we have rho squared sine phi. So rho is rho, but r, if you recall, is just rho sine phi. So that's why we have rho squared sine phi. It's because we have to account for that arc length for both of those circles or cones, whatever we're dealing with. Right? And that's why we have rho squared sine phi. Again, you'll learn more about the Jacobian next class, and then you'll see another reason why we have that. All right, so now all we're going to do, we just need to make sure that we define our regions. Again, our region for theta is going to be the rotation about the xy plane. The phi is going to be given by the rotation from the positive z-axis to the negative z-axis. Again, it's always going to be between 0 and pi. And then our rho is just going to be the difference between, our two circles or cones. All right, so a lot of times you're going to just see, it's going to use the radius for that. All right, so we're going to set up the triple integral of an arbitrary continuous function in cylindrical or spherical coordinates of the solid shown. So here's our solid. And all we're going to do is we're going to write this as a triple integral. And again, when we're going to write this one, we're going to write, what always comes first and to always what comes last. So what's going to come first is going to be our phi. So again, phi is the angle measure from the positive z-axis. So here I'm just going to show you. So that's 0, and then all the way to pi over 2. So it does a half of a rotation. So then that's just going to be 0 pi over 2. Theta is going to start at pi over 2 and go all the way to 2 pi. So pi over 2 to 2 pi. And then we're told that we go from 1 to 2. So our phi is going to go from 1. Our rho is going to go from 1 to 2. All right, of our function is f of x, y, z. Well, now we're changing everything to spherical, so it's going to be f of our x, rho sine phi cosine theta, y, rho sine phi sine theta, and then our z, which is going to be rho cosine phi. Rho squared sine phi d rho d theta d phi. All right, and that's it. That's all it takes to set that up. And then again, working in spherical is going to be so much easier than working in rectangular when we're trying to integrate these. All right, example 6. Evaluate the triple integral 9 minus x squared minus y squared dv, where h is the solid hemisphere of x squared plus y squared plus z squared is less than or equal to 9, and z is greater than 0. So what I'm going to go ahead and do for this one, I'm going to go ahead and I'm going to draw it. Now again, you might have the picture in your head and you might not need to draw it, and that's fine. But, I just want to draw it for the notes so that everybody can see. So what we're told that we're in the positive hemisphere. So now I'll go ahead and just draw the whole thing. So basically, we're just, you know, the sphere above the plane, above the xy plane. It's going to be solid because it's less than or equal to 9. And so, you know, our radius is going to be 3 of the circle. And so we're just going to, you know what I'll do? I'll just draw. Yeah, well, so we just have this circle above. And there's all a distance of 3. And so, you know, we have that solid region above where we have a distance of 3 all the way around. All right, so that's just, you know, to help set up the integral. Again, you didn't have to draw, especially this one. It's pretty easy. So again, we're going to do our phi, so our rotation from the z-axis. So our rotation from the z-axis is 0, pi over 2. Our rotation from, you know, on the xy plane, it's a full rotation, so 0 to 2 pi. And then our rho is just going to be 0 to 3, because that's going to be, you know, our radius around. Now we're going to have 9 minus x squared. So we're going to have 9 minus rho squared sine phi squared cosine squared of theta. And we'll say plus, I'm pulling the negative outside, plus rho squared sine phi squared cosine sine theta squared. And then now I need to include my rho squared sine phi d rho d theta d phi. All right. And again, put that right there. All right, one thing I want you to see, because I don't have a lot of room here, is they both have rho squared sine phi squared. So I can pull that out. If I pull that out, what's going to happen is cosine squared theta plus sine squared theta is going to be on the inside. Well, what's cosine squared plus sine squared theta? Well, that's just 1. So what I have, again, I'm going to have to write all this over and over and over again. So again, you can skip as I just write down. So I'm going to have 9 minus, you know, I can just show it to you. Rho squared sine squared phi. I'm just going to show you it and then erase it. I'm going to pull that out, and I'm going to be left with cosine theta plus sine squared theta. Recall, all this right here is just 1, so I can just go ahead and, you know, erase this and say, that's just going to be times 1, or just keep that there. And then I'm going to have rho squared sine theta d rho d theta d phi. But I'm also going to say, well, you know what? Why don't I just go ahead and multiply rho squared. I mean, I can go ahead and multiply rho squared sine phi. So that's what I'm going to go ahead and do. I'm going to go ahead and distribute rho squared sine phi. Yeah, that should be sine phi. So that should be sine phi into my function. And so then I'm just going to have this 9 rho squared sine phi plus Add rho squared, so rho to the fourth sine cubed phi. And that's going to be d rho d theta. I'm sorry, yeah, d phi. All right, now let's go ahead and integrate with respect to rho. So we're going from 0 to pi over 2. Do I have room? I'm going to get a little bit of room. 0 to 2 pi. That's just going to be 3 rho cubed sine phi. Plus 1/5 rho to the 5th sine cube phi. From 0 to 3 d rho. Not d rho, d theta, d phi. All right, we'll clean that up a little bit. When we clean that up, substituting in 3 for rho, it's really 3 to the 4th, so 81. So we're going to have 0 to pi over 2, 0 to 2 pi, 81 sine phi plus, put the 3 in there, 3 to the 5th power is 81 times 3, 243 over 5, 43 over 5 sine cubed phi d theta d phi. What's good about this is that I have no theta terms, and so I can break this up to just be, do I have enough room for that? I think I do. 0 to pi over 2 d theta times 0 to 2 pi d theta. 0 to 2 pi d theta times 0 to pi over 2. And now all my phis. So 81 sine phi plus 243 over 5 sine cubed phi. These phis are killing me. D phi. And now let's just go ahead and integrate. So the first one again is just going to be 2 pi. Then we do the whole thing because it's going to give us theta. Times, actually I'll just write that out. So theta 0 to pi over 2. 0 to 2 pi. And then times, I'm going to integrate this last one. 81 sine theta is going to be negative 81 cosine theta. Sorry, it's cosine phi. Oh, great. I got sine cubed. And so, yeah, I'm not going to have the space. Okay, I'm going to change this here. So this integral can be rewritten this way. 0, give me some more room. 0 pi over 2, 81 sine phi plus 243 over 5. Since it's sine cubed theta, I'm going to write that as sine squared theta times sine cubed phi. I'm going to rewrite that as sine squared phi times sine phi. So I can integrate this, and sine squared phi is just another way of saying 1 minus cosine squared phi times sine of phi. Again, this is also that I may integrate d theta. It should be theta, so d theta. And now I'm going to integrate that over here on the right. So I'm just going to have minus 243 one thing I'm realizing too here, and it hasn't, we haven't needed it yet, but that should be minus instead of plus. So minus, 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 minus. So it should be minus. So we have minus 243 over 5. And then we have we'll do the integration of the inside. So 1 minus cosine squared phi. If we multiply inside, we're going to get sine theta. So if we get sine theta, we get negative cosine theta. And if we do negative cosine squared theta, we do the inside, we're going to get negative, so positive cosine. We have that squared, it's going to become cubed, so it's 1/3. So it's 1/3 cosine cubed phi minus cosine phi from 0 to pi over 2. Plug that in, we're going to get 2 pi times, plug in our pi over 2, cosine pi over 2 is just 0 minus, we could plug in our pi over 2's, we're going to get 0 minus 0, which is 0, so that's just going to cancel out. Plug in 0, and we're minusing all that, so it's going to be plus 81. And then another plus, plug in 0, so 1/3 minus 1 is negative 2/3. But we have that plus there, so 243 over 5 times negative 2/3, and that's going to give us 486 over 5 pi. So yeah, that was not fun.